Mhm. Okay, 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 good. Um, Welcome, everyone. Uh, let's continue with the seminar. So today I have finished with exercise 2 from classwork 4. So this is classwork 4 and exercise 2, right? I had to do this one, but I did not, so let's do it today. Well, here we have to make a finite sketch for the diagram of the relation of this relation A B on the set of the natural numbers. Okay, so what kind of relation is this? So we know that this pair, the order pair AB, belongs to this relation if and only if there exists some natural K such that B is equal to AK, A times K. Okay, so this is the definition of this relation. Okay, and then we have to make a finite sketch for the diagram of this relation. Okay, so I think we can do something like this. We have here 0, 1, 2, 3, 4, 5, and so on, right? Okay, so we have to find the arrows that we have here. So first of all, of course, since we have that we can, for K1, we obtain that A and B are equal, right? So we always have like this. So the pairs 0 and 0, 1 and 1, 2 and 2, and so on. Okay, so we have this, something like this. Okay, and so on. Good. Now we can see that so if we for yes, so we can, if A is 1, then we can get from 1 to any B, right? So we can K is, in this case, is going to be B, so AB is going to be, if A is 1. So from A we have all these lines to, from 1 we have all these lines to all the others, right? Including 0, right? And so on. And then for 2 we have all the even numbers. So 2, 4, 2, 6, 2, 8, 2, 10, and so on. Okay, and all of them. So if it doesn't matter what A we have, if we multiply this by 0, then we will obtain 0, right? So all the numbers, all the naturals have an arrow that finished with the 0 here. And for all of them, right? Something like this. So we know that, so we have this kind of thing. So any A here and B is going to be just 0. We have this for all A, right? And that's it. So we can see that the number with the least number here, where some arrow begin, is 0, and the greatest is 1, right? And then if we have some prime number, right, some prime number, then this is going to be also just one arrow is going to come to this number. Okay, yeah, and something like this. Okay, it's just to not forget about the definition of this, and yeah, I think it's something like this that we have here. Okay, next. Možete ma predstaviti televizorni работает? Не знаю, просто может вопрос есть. Okay. Good. Thank you. Okay, so now we can continue with coursework 5, right? And we already did exercise 1, so we have to continue with exercise 2. And let me do that. So for exercise 2, we have the following. We have that R is a functional relation, right? R is functional. Okay, and then for any sets x and y, we have that the pre-image of the intersection, yes, of x and y is equal to the pre-image of x intersection the pre-image of y. Okay, so we have to prove that for any two sets here, if R is a functional relation, then we have this equality here. Okay, and we already proved that for so if you check exercise 8C in classwork 4, so you can check this exercise 8C in classwork 4. We already did this one, right? But for so we say that this is a subset of this set, so that this set is a subset of this set. We proved that, okay? And we prove it for any R, for any relation. So of course, if we have a functional relation, it doesn't matter because we prove it for any relation, so this works here. So we already proved this. And since we want to prove that they're equal, then we need to prove in this direction as well. So we need to prove that this set is a subset of this set, okay? So let's do it. And so we are going to take some element from here, right? Some element from this set, and we need to get that this element will be an element from this set as well. Okay, so let's take some element A. So A is an element of this set. So we have that A is an element of this set. And this is true if and only if, well, we have intersection here. So if A is an element of R minus 1x and A is an element of R minus 1y. Okay. So we change just the intersection by and. Okay. And then what does it mean? If I know that A is an element of the pre-image of X, it means that there exists some B such that B is an element of X, right? And B R minus 1 A. Okay, so this is the definition. So if we have that A is an element of this set, then it means that there exists some B such that B is an element of this set X, and we have that BA, the order pair BA belongs to the set R minus 1. Okay, and the same for this one. So, and there exists some, let's call it C, such that C belongs to Y, and C R minus 1 A, right? Yes. Okay. So, and now we have that. We can just, we have two, we have this quantifier and this quantifier, everything is, so this is and here. So we can just unite everything and just take the quantifiers out. So we can write that there exists some B and there exists some C, such that, and we write everything that is written here, so that B is an element of X and C is an element of Y, and B R minus 1 A and C R minus 1 A, right? And okay, now we have this. And what do we need to prove? We need to prove this. Yes. And what do we know about R? We know that R is functional. So let's remember, what does it mean that it's functional? It means that if I have, for example, here, I don't know, X and Y, and here Z, then this kind of relation, so the pairs, if this is, I don't know, from A and B, right? And we have that this is R, okay? So this is not allowed. This is not allowed if we have that R is functional, right? So if we have that X, so we have that X, Z belongs to R, and X, Y belongs to R, it means that, and Y, Z, it means that X is equal to Y, right? So in this case, we have that. We have, well, if we have that R is functional, then R minus 1 is injective, right? So, so here, so since R minus 1 is injective, right? So we have that R is functional. It means that R minus 1 is injective, okay? And then we have to change the meaning of this, so then this is not possible, right? So A, B, and C here, this is not possible, right? So it means that if we have, look, BA and CA, so B is equal to C, okay? No, sorry, I was telling you the other way. Yeah, so this is now for functional. For functional, it means that it's not possible, and for injective, it means that it's not possible. Okay. So again, if R is functional, then this is not possible. Okay. If R in this case, since R is functional, it means that R minus 1 is injective, and for for any injective relation, we know that this is not possible. Okay, so we have that since R minus 1 is injective, then B is equal to C. Okay, yes. So then we obtain that then let me write that here. There exists some B, right? So we have that B is equal to C. We can take just B or C, it doesn't matter. So there exists some B such that B is an element of X and B is an element of Y, right? And B R minus 1 A. So we have that B is an element of X and B is an element of Y. It means that B is an element of the intersection of X and Y. Then we can write that there exists some B such that B is an element of the intersection of X and Y, and B R minus 1 A. Okay, and now we have to go back to the definition of this. So what does it mean? It means that A is an element of the image, well, of the pre-image, right, of the intersection of X and Y. Right, by definition. So if we have that there's some B, and this B forms some order pair with A that belongs to R minus 1, then it means that A is an element of the image of R minus 1, or the pre-image of R. Okay, that's it. So we have that. So we proved that if A belongs to this set, here, then A belongs to this set. So it means that the set R minus 1 X intersection with R minus 1 Y is a subset of R minus 1 intersection of X and Y. And since we proved this, so we proved this and we proved this, it means that these two sets are equal. Okay, so this is equal to this thing here. Okay, and we finish the proof. And that's it. So again, if we have this, so this thing here is true only if R is functional. If R is not functional, then this is not true, right? It's true this. This is true only this case if R is any relation. Okay, good. So this was exercise 2. Let's continue then with exercise 3. So this was exercise 2. Exercise number 3. So what do we have here? We have that. So we have that there's some relation from A to B. R is a relation from A to B, and R is total. Okay, so if R is total, it means that the domain of R is equal to the set A, right? And then we have to prove that for all X, where X is a subset of A, holds that X is a subset of R minus 1 of R of X. So we have to prove that this is true, and we have to check for this as well. So we have to check if they're equal, if X is equal to this, right? But right now let's prove just that X is a subset of this, okay? And we can see this from look. So if we have, so I don't know, imagine that we have R here. So this is A and this is B, right? We have A and B, and we have some relation between the A and B. And let me have just, I don't know, 3 elements here. Three elements in A, and we know that all we know is that R is total, right? So what if we have, for example, here just 2 elements? So we can have this. This works. So this is R. So we have that R is total here. It's total, yes. And yeah, that's all we have that R. So that's good. But we can see that, so if this is X, let's take this X. This is a subset of A, X. We see that the image of X is going to be this. this is the image of X, right? And now what's the image? Well, yeah, what's the image of the image? So what's the pre-image of the image? So this. So if this is R, it means that this is R minus 1, and this, and this thing here. So we obtain that this set, this is the image of the image. So we see that X is a subset of this set here. Okay, we can say that from here. So this is true. I mean, this is not the proof. This is just the way to show you that this is actually true. So X is a subset of this, yes. But from here we can actually, so we build some example in which this is not a subset of this. So they are not equal actually. Okay, but we will show that. So let's show this. Okay, so we need to prove what? We need to prove that X is a subset of this. So let's take some element from X and let's show that this element belongs to this set as well. So A is an element of X, right? And since, what do we know from R? We know that R is total, right? So R is total. And since R is total, it means that there exists, I mean, well, I can write here that for all A, for every element A in X, since R is total, then there exists some B, such that B is an element of B, of capital B, and AB belongs to R, right? So this is true because R is total. So for every element A from here, there exists some B here, such that AB is an element of R. Okay. And then, so it means that this B actually, so that there exists some B, and this B is not just an element of capital B, but B is an element of the image of X, right? Since A is an element of X, right? And then, and A R B or B R minus 1 A. So B R minus 1 A. Okay. And finally, what does it mean? It means that, so this means that A is an element of what? If is an element of the image, well, actually of the pre-image of what set? Of this set. So of the image of X. Right? So we obtain that every element in A is an element of this set as well. So X is a subset of R minus 1 of Rx. And it's proven. So we already proved this, okay? And now we have to show that they are not equal. So that this is not true, and we can see it from here, but we can show you, I can show you some example with some specific sets here. So let me take, for example, take A equal to the set of 0 and 1. Take B, the singleton of 2, and take R. The relation is going to be the following. It's going to be 0 and 2 and 1 and 2. Okay. So we have, so R is a relation between A and B, of course, the Cartesian product of A and B. So we have just 0 and 2 and 1 and 2, right? 0 and 2, 1 and 2. Now, what do we have for, and take X, the singleton of 1. Okay, so X is a subset of A, right? Because the element here is 1, and we have that 1 is an element of this set as well. Now, we can show from here that what's going to be R of X. R of X going to be 2, right? The singleton of 2. So we have to look at the image of X. X is just 1, the singleton of 1. So we look at this, and we have that the image is going to be these 2 here. Okay. And what about R minus 1 of 2? So the pre-image of the singleton of 2, we have for this case 1 and 0. So this is equal, let me write here, 2, 1, and 0. Right? So the pre-image of 2 is 1 and 0. So what did we obtain? That if we have X, so look, so R minus 1 of Rx is equal to 1 and 2, the set of 1 and 0, the set of 1 and 0, and X is equal to 1, right, the singleton of 1. So we can see that this is not a subset. So so this thing here is not a subset of this, right? So this is an example, and we show that this is not a subset of this in the general case. We only had to find some example, some case, and this is the case. Okay, good. So this was exercise number 3. Let's continue with exercise 4. I continue over there. Yeah. So exercise 4. For this one, we have two functions here, f and g. So f, one second, is a function from a to b, and g is a function from a to b as well. So do not forget that what is a function? A function is a relation which is functional and total. Okay, so a function. So a function is a relation which is functional and total. Okay. So, and if it's a function from a to b, it means that f is a subset of the Cartesian product of a and b, right? And so this is the definition of a function, but do not confuse this one with the definition of a partial function. So every function is a partial function, but not every partial function is a function, okay? Because the only requirement for a partial function is to be functional, right? But not to be total. So it can be functional but not total. So it can, not every partial function is a function. Okay. So we have two functions from A to B, and we need to prove. So prove that we need to prove the following: that the intersection of f and g is a function as well from A to B, if and only if f is equal to g. Right? So again, we have two functions. F, this is g, right? Both functions are from A to B, right? And there's another function that does the intersection of f and g. And this is a function if and only if f and g are equal. Okay, if they are the same function. And this is not difficult to see because function means that it's, first of all, functional, right? So that so this is not possible, right? We have here something. So from A, B, and C, right? So this is not possible. So if we have something like this, it means that B and C are equal, right? And a function is total, then this works for all the elements in A. So they have to be equal. But let me prove it anyway. So we have to prove here two directions. So we have if and only if. So let's prove this direction. So let's assume. Let's assume that f is equal to g. If f is equal to g, right, then the intersection of f and g is going to be f or g. I mean f and g, right, the same. And we know that the f and g is a function from A to B. So that's it, right? That's it. So in this direction is very easy. Okay. Now in this direction, by the way, that's important because a lot of you in your homework had to prove many times that if and only if. But do not forget that if you're proving if and only if, it means that you have to prove two implications, right? Do not forget that, please, because I had problems with many of you because of this. Two directions have to be proved here, okay? Good. Now, let's assume that this is true, and let's find that they're equal. Okay, so this direction. So let's assume, assume that the intersection of f and g is a function from A to B. So let's assume that the intersection of f and g is a function from A to B. Okay. So we have to prove. I need the following. I need to show that f is equal to g. Okay. And it means that I have to prove always that f is a subset of g and g is a subset of f. So if I achieved to prove this, it means that they are equal. So let me try to prove it. And let me do it here, these boards. Oh, no. Yeah, this one. Okay, so let's prove this. Let's prove that F is a subset of G. Okay, so do not forget, functions are sets of ordered pairs. So yeah, a function is a set. Everything is a set here. So we have to prove that this set that we call a function F is a subset of another set that we call a function G. Okay, so let the ordered pair AB be an element of F. Okay, so we have some element of the function F. Now we have to show that this ordered pair AB belongs to G as well. So so we have that. What do we know? We know that. So we know that we are assuming that the intersection of F and G is a function from A to B. It means that the intersection of F and G is total and functional. So since, let me write here, so the intersection of F and G is total, right? So it means that there exists some C in B such that AC is an element of F intersection G. Okay? So again, F is a function from A to B. So for all the elements A from capital A, we have defined these ordered pairs A, B. Now, since this function here, since this intersection is a function, then it's total. It means that for this A here, there exists some C in B such that AC is an element of this function. Okay? Now, so it means, so since we have that AC belongs to the intersection of F and G, then it means that there exists some C such that C is an element of B, and AC belongs to C and AC belongs to G, right? To the intersection, so it belongs to both of them. And we know that F is functional, so F is a function, so it's functional. So since F is functional, then we have that loop. We have that AB is an element of F and AC is an element of F. So we have AB and AC. What does it mean? Let me write that here. AB is an element of F and AC is an element of F. It means that B is equal to C, right? B is equal to C. And from here, so we have that since B is equal to C, and we have this thing here, we can write then AB is an element of G, right? And so we obtain that for every ordered pair AB and F is an ordered pair in G. So F is a subset of G. The function F is a subset of the function G. Okay? How do we prove in this way? So how do we prove that G is a subset of F? The same way, okay? So we have to write exactly the same. I'm not going to do it because it is exactly the same. So everything is similar. Okay, everything is similar, and then we obtain that f is equal to j. And we're finished with the proof. So we proved both directions here. This direction was very easy, right? And this one, well, not complicated at all, right? And that's it. So we proved. So we finished with exercise 4. Let's move to exercise 5. So do not forget, please, that next week is your deadline for homework 2, and then you will have homework 3, number 3, okay? And this homework will be on functions, of course. And the deadline for homework 3 will be in the middle of January, okay? And the next seminar is the last seminar. I will finish with classwork 5, and that's it. So we don't have more classworks for this semester, because the next semester we continue with this class. The name of the class is going to be different. So this class is called Mathematical Thinking, and the next semester is going to be called Introduction to Logic, or Mathematical Logic, or something like that. Okay, but it is exactly the same. So we just continue with this course. Okay, good. So this was exercise 4. Yes, now we have to continue with exercise 5. So again, we have two functions, f and g. But now, so we have function f from a to b, and the function g from capital B to capital C. Okay, so something like this, a, b, and c, right? So we have here f, we have here g, and this is a, b, and c. So we have these two functions, and so we have to prove that if G composition F is a surjection, if G composition F is a surjection, then G or F, G is a surjection as well. So G composition F is a function from A to B. So this is G composition F. G composition F, right? So we have to prove that if this is a surjection, then G is a surjection as well. So what is a surjection? First of all, is a relation which is a function, and it is surjective, right? So it's a function and it is surjective. So it's something like this. This is a function which is surjective. No, sorry, no, this is not true. Okay. No, now it's true. Yeah. So this is a function which is surjective. Okay. So it means that for every element in B, for example, in this case, there exists some element in A such that, I don't know, AB belongs to R or to F or whatever, okay? So we have that, and we have that this composition here, G composition F, is surjective. Okay, so let's prove it. So let me write the following. So we have that G composition F. So this is given, right? What is given? It's given that G composition F is a surjection. So this means that for all element in C, there exists some element in A such that X, Z, these two elements, this order pair belongs to, well, to G composition F, right? And we need to show that G is a surjection as well. So that for every element in C, there exists some element in B such that this order pair belongs to G. Okay. So we have this, we're given with this, and we need to prove this. Okay. So let's use this, and we obtain the following. So we have that for all the elements in C, there exists some element in A such that this order pair belongs to the function, the G composition F. So we are given with this. And this is true if and only if so we have this, right? Somehow let's show by definition what is the meaning of this. So this is true if, again, we have to write this. So for all the elements in C, there exists some element in A such that, and here we have to write, there exists some Y in B, right, such that xy belongs to F and yz belongs to G. So this is just the definition of the composition here. Okay. So, and this means we can just take into account. So let's forget about x. Let's forget about x and let's take only the elements from C and from B. So this is true. So this implies that for all the elements in C, there exists some y in the B such that yz is an element of the function J, right? So this is given. Then by the definition of the composition of G and F, we have this, so that there exists some y in B such that this holds. And then this thing here implies this, right? We just forgot about x, but everything is true here. So, and what is this? right? So it means that, and this is true if and only if G is a surjection, right? Because we are saying that, so what is written here, it's the same that we have here. So that what we need, right? So we using this, we obtain this, then this is proof. Okay. So we obtain that G is a surjection as well. Good. So this was exercise 5. Let's continue with exercise 6. Exercise 6. Okay. So we have proved that a function f from a to b. So we have a function from a to b. And if a surjection, if and only if what? For every set C and for every functions, so if for every functions G and H from B to C, it follows that G is equal to H. So we have to show that this implication, if and only if. So this if and only if with this one, so if set surjection. So we need to prove that if F is a surjection, then this implication here holds, right? And if this implication holds, then F is a surjection. Okay, so again, since we have to prove if and only if, then we have to prove this in two directions here. So let's prove it. And let's prove it first for this direction. So let's assume, so we have that, so here we have that F is a surjection, right? We have that F is a surjection, and we have that, wait, I forgot something. Yeah, I forgot the main thing here. Right. So Johnson will be, okay. No, let me rewrite this. The implication is not like that. The implication is the following. So if I have the function 8, f is a function a to b, and g and h are functions from b to c, then we have that f is a surjection, if and only if for every C and for every G and for every H, we have that from this. So if the composition of GF is equal to the composition of HG of HF, follows that G is equal to H. Now it's correct. Okay. So again, I have a function f which is surjective, okay? And I say that if this function f is surjective, then this implication false. Okay, so that if the composition of f with two other functions is equal, then these two functions are equal. Okay, and I have that if this implication is true, then it means that f is surjective. Okay, so think about this by a moment. It's not that trivial. Okay, but yeah, we'll see it. So let's prove this. Now we can prove it. So let's prove this direction. So let's assume that f is surjective, and let's assume that that this holds, but that g and h are not equal. So let's assume that f is a surjection and that g composition f is equal to h composition f. And let's assume that g is not equal to h. Now we need to get some contradiction here, right? Because we're assuming this, we're assuming that this holds, but we're assuming that they're not equal. So, so since they are not equal, and let me write that. So we have that here. We have b and c. So no, b here, c. So g and h are functions from b to c. So it means that there exists some b in capital B such that g of b is not equal to h of b, right? Since they are not equal, so these two functions g and h are not equal, it means that at some point the value for b is not equal in these two functions, right? And then it means, but look, but since f is surjective, so we have that f is surjective, then there exists some a in capital A such that f of a is equal to b. Right, so we have f, so if we have here b and c, so we have here a, and this of f is a function from a to b. So f is a function from a to b, and f is surjective. It means that for this b, right, for this b and b, there exists some a such that f of a is equal to b. Okay, and then we obtain the following. We obtain that g of f of a is different from h of f of a, right? Because f of a is b. This is what we have written here. We just write f of a here, b and b. And they're different. But we assume that they're equal, that the composition is equal, and we obtain that they're different. So we obtain a contradiction here. Okay, so it means that g, so g is equal to h. And we proved this in this direction. Okay, so equal. Yes. So again, we got the contradiction. Hey, look, this is a contradiction with this. You showed in your lecture that if we have functions and we talk about the composition of functions, then we're talking about this. So this is the composition of G and F. Okay, good. So we prove for this direction. So now let's prove it for the other direction here. Now let's prove for this direction. So we have to show that if this is true, then F is surjective, right? So let's find some. So let's assume that F is not surjective, and let's show that in that case we can find always such G and H such that their composition are equal, but they are not equal. So if we achieve to show that for F non-surjective, we find such functions such that this doesn't hold, it means that if this holds, then F is surjective. Okay? So we take the implication here and we change it for the opposite, and they're equivalent somehow. So let's assume that F is not surjective. Okay, and so then if we assume that F is not surjective, then the implication this implication, right? Should fail. So if F is not surjective, then this implication should fail here. If we can show that, so if we can find some G and H such that they are not equal, then everything will be proven. Okay. Okay. So let me write that. Let's find some G and H such that G composition F is equal to H composition F, but H is not equal to G. Yes. So if we can find that, that will be it. So let's take the form. Let's see be equal to the set of 0 and 1. Okay, and now since we have that, so again here we have that F is a function from A to B. A is a function from A to B, and G and H are functions from B to C, right? So we have that C is 0 and 1, so we only have two elements here, 0 and 1. Okay, and now since F is not surjective, then it means that there exists some B prime here in B such that it doesn't belong to the relation F. Okay, so some B prime that there exists some B prime such that B prime belongs to B, so the difference from B and the range of F. Okay, so the range of F is not the set B completely because F is not surjective. So there exists some B prime here which is not covered, let's say like this, by this f. Okay. And then let the following, let g of b be equal to 0, and for all b in capital B. So the function g is going to be just for all b, there will be 0. And now the function h will be for b prime will be 1, and for h of b will be 0 for all b different from b prime. Okay, so we define completely these two functions, g and h. Okay, so g of b for all elements of b is going to be always 0, and h of b is going to be 0 as well, except for b prime when it will be 1. So we see that these 0 and 1, these are the elements of C. Okay, and now from this follows that g is not equal to h. Okay, and but they are not equal. But what we can see that for all a in A, f of A is not equal to b prime, then g of f of A is equal to h of f of A. So they're equal to 0. Right? So for every element in A such that f of A is not equal, I mean for every element of A, we have that f of A is not equal to b prime, because b prime doesn't belong to the range of f. So it means that these two, this f of A here and this f of A are just b. So this is b different from b prime, and this is b different from b prime. So, and we have that for b different from b prime, for g and h, we have that this is they are equal to 0. So we have that g in composition f is equal to h composition f. That's it. We prove it. So we found some h and g such that the composition here, this composition are equal. F is not surjective, but the function itself are not equal. And this proof this direction. Okay, we're finished with this one. Now this was exercise 6. Now we can move to exercise 7. Okay, exercise 7. 7. Exercise 7. So, under which condition does it follow from b to the a equal to g to the c? It means that a is equal to c and b is equal to d. So we have that these two sets here are equal, and we want to find the conditions for which, if we know that they're equal, then it means that a is equal to c and b is equal to d. But first of all, let me remind you what is this. So we have that A, B, C, and D are sets, right? And so what is this? What is B to the A is equal to what? Well, this is all the functions these are all the functions f such that f is a function from A to B. And that's it. So this is the definition of B to the A. Okay, so this is the set. B to the A is the set of all the functions from A to B. And in the same way, we have this. So D to the C is the set of all the functions from C to D. Okay? And now we have to show in which case we know that this is true, that this implication holds. Well, all we need here is that A is not empty and B is not empty as well. Okay, so this is all we need. Why? Well, if we know that A is not empty and B is not empty, then it means that D is not empty and C is not empty, right? Why? Because look, so these functions here, these functions are elements of the power set of the Cartesian product of A and B. Okay, so and the Cartesian product of A and B. So let me write that. For all A, we have that the Cartesian product of A with the empty set is empty, right? We proved this already. So we know this. And it's the same if, I mean, the empty set Cartesian product with A is going to be empty as well. So we have that if in the Cartesian product we have an empty set, then this is going to be empty. Okay? So if these two sets are not empty, then this B to the A is not going to be empty. It means that D to the C is not empty, so D is not empty and C is not empty as well. Okay? And okay, so let's suppose that we have this. So it means that D and C are not empty, that's good. But still we have to prove that A is equal to C and B is equal to D. Okay? So let me do that the following way. So let's take some f. F is a function that belongs to, is f. Let's take a function from A to B. So an element of this set, B to the A. Okay, so f is an element of B to the A. So f is a function from A to B. And we know that B to the A is equal to D to the C. So it means that f is an element as well of D to the C. Okay. And what does it mean? So if we have a function from A to B, f, it means that the domain of f, since f is a function, then f should be total. So the domain of f is A, because f is total. Okay. And in the same way, the domain of f in this case should be equal to C, right? So the domain of A is equal to C, so we obtain that A is equal to C. Okay? This is by just from the properties of a function of being total, of being functional. Okay? And now, what about, so we have that A is equal to C, what about B and D? So let's take some, so for all B in capital B, right? So B to the A is a function from A to B. So let's take all the elements from B and let's define the following function. F sub B let's define the following function f sub b. Okay, so this is a function from a to b. And this is a function such that for every element in A, f sub b of A is just equal to b. Okay, so for every element b in capital B, we define a function f sub b such that f sub b for every A is just b. Okay, so something like this. So this is b here, this is f of b, going to be just this. Okay, and we have to do it with all the b's, all the possible b here in b, in capital B. So then we'll have, this is b prime, and we have this. This is f sub b prime, and so on. So this is for all the b in capital B. And so since this function is, since this is a function from A to B, and b to the A is equal to d to the c, then f sub b is an element of d to the c as well. So f sub b is an element of, so it's a function from c to d as well. So it means that b, this element b, should be an element from d, right? Because so the function gives us b, and so all the b that are in B should be in D. So we obtain that for every element in B is an element of D. So B is a subset of D. And in the same way, if we change this B for some D in capital D, we do exactly the same. We obtain that D. So similarly, D is a subset of B. So B is equal to D. And we prove it. So we prove that if A and B are non-empty, so A is equal to C and B is equal to D. Okay. But what if, anyway, what if some of them, of these two sets, is empty? So what if A is empty, for example, right? Then we obtain that B to the A is going to be empty as well, right? And this is equal to D to the C. So we can obtain, for example, that that C is empty, right? So we obtain, yeah, that A is empty and C is empty, and B to the A and D to the C are equal because both of them are empty. But this doesn't mean that B is equal to D. So B is different from D in general. In this case, because they can be any sets different from each other. So B and D can be any sets different from each other, and we will obtain this. And the same for B being empty. Okay, so for A empty or B empty, this is not true. This condition doesn't hold. And we are done with this proof. Okay. So we have exercise 8, but this is a long one, so I don't want to start it just like that. So this one will be for next time, for next seminar. That is the last seminar. So thank you very much.